everyone. In this section, we introduce the fundamental theorem of arithmetic, which basically claims that an arbitrary natural number that is greater than or equal to 2 can be uniquely decomposed as a product of prime numbers. More precisely speaking, the theorem states the following. Let n be a natural number that is greater than or equal to 2. Then there exist r different prime factors, namely p1, p2, p3, until pr, listed in an ascending order, as well as r positive exponents k1, k2, until kr, such that n is equal to p1 to the power of k1 multiplying p2 to the power of k2 multiplying p3 to the power of k3 until pr to the power of kr. Moreover, such decomposition is unique. Here, the meaning of uniqueness is twofold. First, the choice for these prime factors is unique. Second, the exponent for each of them is also unique. For instance, 7 is a prime number of its own right. Thus, we can write 7 as 7 to the power of 1. 24, on the other hand, is a composite number, whose prime decomposition is given by 2 to the power of 3 multiplying 3 to the power of 1. Similarly, 360 is also composite, where the prime decomposition is given by 2 to the power of 3 multiplying 3 to the power of 2 multiplying 5 to the power of 1. Notice that in the statement of this theorem, we have requested that all these prime factors p1, p2, and p3 show up in an increasing order. This is to ensure the uniqueness of such a decomposition. Otherwise, the permutation among different prime factors will not change their product. For instance, we have seen that 360 is equal to 2 to the power of 3 multiplying 3 to the power of 2 multiplying 5 to the power of 1. And if we actually flip the prime factors 2 and 3, we get another presentation which reads 3 to the power of 2 multiplying 2 to the power of 3 multiplying 5 to the power of 1. Since the multiplication is commutative, both representations are equal to the same number 360, which brings some ambiguity to the uniqueness. And we can avoid such unpleasant phenomena by simply imposing this ascending order on our prime factors. Also notice that given an arbitrary prime number p to the power of 0 is always equal to 1, and if we multiply 1 to a number n, we still end up with the same number. That is why we need each of these exponents to be strictly positive integers. Otherwise, we may again lose uniqueness. For instance, 360 can also be written as 2 to the power of 3 multiplying 3 to the power of 2 multiplying 5 to the power of 1, then multiplying 7 to the power of 0. And that is why we have insisted that all the exponents be strictly positive. This theory is called fundamental theorem of arithmetic, not for nothing, because this decomposition tells us that in number theory, prime numbers are the building blocks. Now, let us discuss its proof. In the following, we will first prove the existence, then the uniqueness. For the existence, let us proceed by mathematical induction. To this end, we first work on the base case where n is equal to 2. Since 2 is itself a prime number, we can write 2 as 2 to the power of 1. This is clearly the desired decomposition. Now let us move to the induction step by assuming that an arbitrary natural number between 2 and k permits a prime decomposition. Let us consider n equals k plus 1 and show that k plus 1 also permits a prime decomposition. We know that k plus 1 is either a prime number or a composite number. So let us discuss these two different cases. If k plus 1 is itself prime, then the decomposition is clearly k plus 1 to the power of 1. And we're done. Otherwise, k plus 1 is composite, meaning that it has other factors other than 1 and k plus 1 itself. In particular, we can write k plus 1 as the product of two integers a and b, where a and b are both greater than or equal to 2, less than or equal to k. Since this is precisely the range where the induction hypothesis holds, we can apply the induction hypothesis to obtain the prime decomposition for a and that for b respectively. Now, multiplying them together, grouping the identical prime factors, and rearranging them into ascending order will produce the required decomposition for k plus 1. Thus, we have finished our induction, and we have proved the existence of the desired prime decomposition for an arbitrary natural number n greater than or equal to 2. Next, let us work on the uniqueness. Let us assume that for some natural number n which is at least 2, we can find 2 satisfactory decompositions. And our mission is to show that these 2 decompositions agree with each other, meaning that they have the same prime factors and the same exponent. Let us first show that they have the same prime factors. To this end, let us denote by set A the collection of distinct prime factors of n in the first decomposition, and B the set of prime factors involved in the second decomposition. Let Pj be an arbitrary prime number from A. Since Pj divides n, by writing n into the product of the second decomposition, we see that Pj divides q1 to the power of L1 multiplying q2 to the power of L2 until multiplying qs to the power of Ls. Now, since Pj is a prime number, the Euclid lemma indicates that Pj divides some qi on the right-hand side. However, recall that qi is also a prime number, whose only positive divisors are 1 and qi itself. Since Pj is a prime number, it is not equal to 1. Thus, we conclude that Pj is equal to qi precisely. Since the choice of Pj is arbitrary in set A, we conclude that set A is a subset of set B. Following a similar argument, we can show that set B is also a subset of set A. Combining these together, we see that A and B are identical, which means that the prime factors involved in both decompositions are the same. As a result, now we only need to exclude any possible differences among the exponents in these 2 decompositions. Let us first show that K1 is equal to L1. And this time let us prove by contradiction by assuming that they are not equal to each other. From there, we can assume without loss of generality that K1 is strictly greater than L1. Now, dividing P1 to the power of L1 on both hand sides, we achieved the identity below. Notice that since K1 is greater than L1, the product on the left-hand side has at least a copy of P1. In other words, P1 divides the left-hand side. Thus, P1 should also divide the right-hand side. Again, according to the Euclid lemma, P1 should divide Pj for some j other than 1. Since both P1 and Pj are prime numbers, we conclude that P1 is equal to Pj. This is a contradiction, as we have assumed all these prime factors are distinct. As a result, K1 must be equal to L1. Clearly, the above reasoning only relies on the primality of P1 instead of its specific value, which means that we can now repeat similar arguments to all the other prime factors P2, P3, P4 until Pr to conclude that K2 is equal to L2, K3 is equal to L3, and so on until Kr is equal to Lr. As a result, all the exponents are identical respectively, and the uniqueness of the prime decomposition is proved as well. As an easy application, let us apply the fundamental theorem of arithmetic just proved to show that the logarithm of 48 to the base 36 is not rational. To prove this, let us assume to the contrary that this number is indeed rational. Since 48 is greater than 36, this number is positive. Thus, we can assume that there exist positive integers p and q which are co-prime to each other, such that this number can be represented by p over q, which, according to the definition of logarithm, means that 48 is equal to 36 to the power of p over q. Now, raising both hand sides to the power of q gives 48 to the power of q is equal to 36 to the power of p. If we apply the FTA to 48 and 36 respectively, where 48 is equal to 2 to the power of 4 multiplying 3, while 36 is equal to 2 to the power of 2 multiplying 3 to the power of 2, we see that this equation becomes 2 to the power of 4q multiplying 3 to the power of q is equal to 2 to the power of 2p multiplying 3 to the power of 2p. So both ends have the same prime factors. So far so good, there doesn't seem to be any contradiction at this stage. However, don't forget their exponents must agree with each other as well. By comparing the exponents of 2 on both hand sides, we obtain that 4q is equal to 2p. Similarly, by comparing the exponents of 3 on both hand sides, we see that q is equal to 2p as well. Putting these two conditions together and solve this system, we see that p and q must vanish. This is a contradiction. As a consequence, we see that the logarithm of 48 to the base 36 is irrational. That finishes the proof.